Hello, hello, hello. So the last video that you looked at dealt with diodes right at the end. If you remember, a diode was an N-type semiconductor and a P-type semiconductor that were glued, basically, not exactly glued, but they were attached to one another. And that what diode did for you, they allowed you to take AC and turn it into DC in the sense that a diode only allows current to flow in one direction. So if you look at this device, what you see is an N and a P-type semiconductor together. So here's a little diode, and an N and a P-type semiconductor. So here's another diode that basically are back to back with one another. And I might add, in the real device that we're going to be discussing here, this section would be wafer thin. I've made it big so you can see it. In any case, if you think about this, you would probably conclude that this would be a pretty useless device. And the reason why is because with this battery set up like so, with this the high voltage side, the electrons in this N-type material would be attracted to the high voltage side on both sides. The holes would be repulsed. This PN junction would have no voltage drop or very little voltage drop across it, but this one would create that depletion zone we were talking about. And for all intents and purposes, you'd have no current flowing through the circuit. Except it turns out that if you were clever, you could actually get current to flow in this circuit. And the cleverness is wrapped up in what how you treat this terminal. The terminal that's attached to the central material. Because if you make this terminal electrically positive, and I might add, this device is called a transistor. And there are two different kinds of transistors. There are NPN transistors, and then there's the other version where this is P, this is N, and this is P. So they're NPNs and they're PNPs. We're dealing right now with an NPN transistor. So for an NPN transistor, if you make this terminal electrically positive, what will happen is that the holes in the P-type semiconductor in this region will be repelled by the positiveness. And the electrons will be attracted. And what will happen is that they will combine and the depletion zone will diminish through here. And the reason why that's kind of cool and useful is that if we go back to our original circuit, this battery is trying to push current through the circuit like so, assuming you're dealing with conventional current. And so without this, with the depletion zone in full flight, so to speak, you aren't going to get any current at all. But if you make this terminal electrically positive and you make some of the depletion zone diminish, now you're going to get a trickle of current through. And if you make this even more positive, the depletion zone will diminish even more and you'll get even more current through. And in fact, it turns out that the amount of current that ends up flowing through is very, very, very sensitive to how big this polarity is. Now, these terminals are given names. The central terminal is always called the base. On an NPN transistor, the terminal in which current flows is called the collector. Okay. Notice that the PN junction between the collector and the base is where the depletion zone is. That will always be the case, both for PNP and NPN transistors. Where the current exits the transistor, again for an NPN, is called the emitter. So that's just vocabulary. You're going to hear those words later on down the line. You just need to know what they are. So how are these things useful? How are they actually used? Well, let's say that you have a signal, okay, some kind of signal. When the signal has this side being positive and this negative, now this terminal is electrically positive. the depletion zone is going to diminish. And depending on where you are in the cycle, because remember, this voltage is going to get bigger and bigger and then smaller and smaller as it goes back down to zero. Depending on where you are in the cycle will depend on how much the depletion zone diminishes and then reestablishes itself, which will be mimicked by the current flow in the circuit. So the current and the voltage basically across this resistor, it'll go up and it'll come back down again in the same way that the signal went up and came back down again. The only problem with this design is that when the signal goes negative, then this terminal goes negative and the depletion zone reestablishes itself, and now nothing is happening. So the clever thing that people do is they put in a bias voltage. The bias voltage is just, it's just a DC power supply. And so here is your signal. But if you add the signal to the bias voltage, you end up with a base voltage that looks like this, which is always positive. So what you have here at this terminal is this voltage that is fluctuating, and it's always positive, which means the depletion zone is continuously fluctuating, which means the current through this circuit is continuously fluctuating. So if you make this battery relatively large and your signal was relatively small, you can get a signal out that looks just like the signal in, but bigger. In other words, what you've done is you've just amplified your signal, your input signal. And that's what transistors do. That is one of the main things that transistors do, especially when they first came out. When I was a kid, my dad was a wonderful person, and he was a very nice man. The only mean thing that he ever did to me, and he wasn't intending to be mean, it was just supposed to be a joke, but when I turned 16, I dearly wanted a car. And I was given, a gift, a little box, and I opened up the box for my birthday. It was on my birthday. I opened up the gift, and inside was a car key. And I went running out of the house around the garage to where the driveway was, and sitting on the driveway was this tiny, tiny, tiny little car. And basically what it was a transistor radio. And it was right when transistor radios first came out. So in fact, it was a pretty cool present. It really was a pretty cool present. It wasn't a car, which would have been an even cooler present, but it was quite a cool present at the time, because at the time, if you wanted to have music, you had to be able to plug the radio into the wall. You didn't have, a little, portable radio that you could stick in your pocket and walk around with your tunes. Okay. There weren't boom boxes. There weren't, stereo systems that you could just walk around with. And the reason why was because signals coming into radio stations, into radios picked up by antennas, they had no way of amplifying the signals so that speakers could be driven by the information coming in from the radio stations, until they came up with transistors. And once transistors came into existence, then they could take a radio signal and they could amplify the signal and drive a speaker that was big enough to actually make sound that you could hear, and voila, transistor radios. And so what that little car was actually a transistor radio, and it was like the first year that transistor radios even came out. So as I said, it was actually a really cool gift. It's just that in comparison to what I was hoping for, it was not as exciting as it might have been otherwise. Anyway, the point is that that's what they do. That's what transistors were originally designed to do, was to amplify signals, and this is the way that they do it. Now, this is basically what a a transistor looks like. Let me get rid of the picture so you can see it here. Actually, I might as well get rid of that too. Oops, no, go away. Okay, so if you look down on one of these things, if you were to look down on one of these things, it would sort of look like a half moon. And so what you're doing is you're sort of looking at it from a three-dimensional view from the side, from the top, kind of semi-looking down. So here is the half moon part. This side is flat. If you're looking at the flat side, the central section is the base, the left is the emitter, and the right is the collector. And that would actually be really important if we were building our little solar robots, because the solar robots actually have two transistors, an NPN and a PNP in them. Obviously, you're not doing that this year, but that's would have been an important thing to know about at the time if we were doing it. What about NPN transistors? So NPN transistors basically do the exact opposite that PNPs NPNs do. A PNP transistor, if this is positive, the holes get shoved this way, the electrons get shoved this way. So this turns out to be the PN junction that doesn't have a voltage drop across it. This is where the depletion zone is. Now, if you remember, we decided the depletion zone had to be along the PN junction associated with the collector and the base. This is the base, which means this must be the collector, which in turn means that PNP transistors are kind of odd in the sense that current enters the emitter and leaves the collector, which is the exact opposite of NPN transistors. So what I normally tell students is if you're going to memorize anything having to do with, how things work, memorize what's going on with an NPN, because NPNs actually sort of make sense. The current comes into the collector, it goes out of the emitter. PNPs are the exact opposite. Let's see. So, and the other thing that's different is that with PNP transistors, you need a negative bias here for things to work. So, symbols. So this is the symbol that you will see for a transistor, and there are three things about the symbol that tell you information you need to know about the transistor. So the first thing that you need to know is whether you're looking at an NPN or a PNP. And the arrow is what tells you that. The arrow always points away for NPN transistors. So this is an NPN transistor. This is an NPN transistor. The arrow points towards this bar for PNP transistors. The second thing that information you're given is the arrow is always attached to the lead that is the emitter. So here is the arrow, and there's the emitter. Here's the arrow, there's the emitter. Here's the arrow, there's the emitter. Here's the arrow, there's the emitter. And lastly, the arrow tells you the direction the current will flow through the transistor if current is going to flow through the transistor. So here it's going to flow like so. 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 And so here is just kind of a summary of that. This is just Ms. Dunham's kind of little summary. You can go ahead and take a look at all that. If you want to stop the video and just take a quick look just to make sure you understand what's going on. Again, here's more questions. So if you want to go ahead and read the question and then take a look at the answer. So there's the answer for that one. You want to stop and look at the second one. There's the answer for that one. Take a look at the third one. Whoops, no answer. That's life. Okay, anyway, I didn't even look to see what the third one was. More important than the polarity of the base, the relationship between various currents in transistor. Okay, whatever. All right, so the last thing that I need to talk about has to do with gain. And so the current that's leaving the emitter, the current that's coming into the collector, and the current that's coming into the base on a NPN transistor, the collector current and the base current are related by what's called the gain. And so the whole idea is that you have a certain amount of input current. That current gets amplified. And so the amplification for a transistor could be like 1,000-fold. And in fact, you can actually sort of daisy chain transistors together to get, huge amplifications. Although you have to remember that when you're amplifying things, you're amplifying everything, which includes, any kind of distortions that might exist. In any case, this is not particularly important, but it happens to be something that is true. So it's being included here. This is just kind of a summary page of some sort of extra kind of things that Miss Dunham decided to throw out, and they're kind of interesting. So one of the points that's important is that to actually get a transistor to cooperate and do pass current, you need a base emitter voltage difference of 0.6 volts for a silicon NPN transistor. And the reason why that's important is it means that you can actually use a transistor like a switch. And in fact, in the little solar robots that you were going to make, that was the way those two transistors that I mentioned, that's the way they were being used. What was happening was in that solar robot was that there was a solar cell that was charging up a capacitor, and at a certain point, these transistors would turn on, and in doing so, they would allow the capacitor to dump their charge through the motor, and the motor would end up taking off for some shorter period of time while the capacitor had charge, and then once the capacitor had discharged, the transistors would turn off, and then the solar cell would recharge up the capacitor until the transistors turned on again, and then the capacitor would dump its charge through the motor. And it was actually it's a very cool design. But the point is that it's using transistors like switches. The thing that I don't normally tell my kids, but Miss Dunham picked up, was the fact that computers actually use millions and millions of these 7-nanometer transistors, and which means that they're like 7 times 10 to the minus 9 meters long. They're on integrated circuit boards, and they actually act as the switches to gate Boolean logic that executes the logical operations that allow your computer to do what it does. Which is pretty amazing. It is funny. I remember talking to a tech like a year or two ago, and I was talking about a transistor, and he was dumbfounded that I was talking about a single transistor, because people who are into computers, they're thinking of transistors being on these integrated circuit boards where you have millions and millions and millions of them, and that's the reason why. Anyway, that's pretty much transistors in a nutshell. And I've just dumped a huge amount of information on you, but it's what transistors are about, and that's why you're here, is to learn. So that's it.